An important property of functions on intervals that we've seen in previous calculus course is that of continuity. Well, first I will give an intuitive explanation what continuity encompasses, and later on I will then give a precise definition what is continuity at some point, and then I will make a statement what is continuity on an interval. So intuitively, I'll look at this function. Well, I is an open interval AB, and I graph the function. The graph of the function is given by this yellow line. You see that the graph of this function can be sketched or drawn without taking the pencil off the paper. Intuitively, that is what makes a continuous function. So this function would point at a continuous one, where the line, the yellow line, the graph of the function is a continuous thing, continuous object. Now look on the right. So here we have a different function, and we see clearly that if we look at some point C at some in the middle of the interval, we see that the function jumps, right? So that the function value, if we close in on C from the left, so if we move from the left to C, then we see that suddenly if we take a small step from C to the right, we jump up, right? So if we would like to draw this graph, we would need to take the pen from our paper, and this is called a discontinuity. So this function is discontinuous. Okay, now I will make things more precise. I give the precise definition that you've seen before in an earlier course. So the definition is the following. So suppose we have I as an open interval, right? So this open interval can be of type AB. It can also be the whole real line, which is also an open interval. And suppose that f is defined as a function on this interval. It's a real valued function. And suppose that C is a point in this interval. Okay, then what is meant by f being continuous at in C is the following, that if for every epsilon larger than 0, there is a delta which may depend on epsilon, such that if we take x in the domain and at distance at most delta from C, then also the images are nearby. The images are close and not further away than epsilon. Right, so epsilon. Should be epsilon here. So, which means that the graph is a kind of continuous. So if we move towards this C on the left, right? So we see this left graph of the function. If we move nearby C, then the images should also be close, right? So suppose we take in this C, so here I have the f of C, and we take an interval around, we take a distance, the fc plus epsilon and the fc minus epsilon, then we should be able to find an interval around C such that all images around C are projected in this interval on the vertical line, right? So we have that all images should be contained in fc plus epsilon and fc minus epsilon, which would mean that the distance from the image fx to fc is smaller or equal than epsilon. So it means that if we take x close enough to C, then the images are also very close. Okay, so that's the essence of continuity. Now we say that f is continuous on this interval if f is continuous in all c in this interval. There's a lot of continuous functions. So here I will just give a couple of examples. And we can use those standard functions to create other continuous functions. So the exponential functions and the logarithms, these are all continuous functions. Also continuous are the sine, cosine, and the tangent, so the trigonometric functions. And the tan h, the sine h, and the cosine h are also continuous functions. Polynomials are continuous, and also rational functions, which are just a fraction of two polynomials. These all give rise to continuous functions, and that's a very nice thing. Also, the absolute value is a continuous function. So there's a lot of functions that are continuous, and having continuous functions, we can create new continuous functions by adding, subtracting, dividing, and composition of functions. So we can make more examples by building products, compositions, and fractions, etc., etc. So these are all continuous functions.